In this video, I'm going to go over the analysis of a flyback converter operating in the continuous current mode. Now, this flyback converter is one of the most popular isolated DC-DC converter topologies out there. It's very widely used. And as you can see in this top circuit schematic of the flyback converter, it's very simple. So we have this transformer here for electrical isolation. And on the primary side, we have an input voltage source and a low side controlled switch. On the secondary side, we have a diode, an output capacitor C, and a load resistor R. Now, to begin our analysis, we're going to use an equivalent electrical circuit model for this transformer. And that's represented by this model here on the bottom, this transformer. And in this model, we have an ideal transformer with the N1 to N2 turns ratio. And we also have a magnetizing inductance Ln that represents the energy storage of the transformer. Now, for this analysis, I've drawn out the quantities of interest. So we have these various values of voltages and currents labeled in blue. So to start off the analysis, we're going to look at the circuit in state 1 and state 2. So that is the state when the switch is turned on and the state in which the switch is turned off. So let's start off with state 1, which is the DT interval in which the switch is closed. And I'm just going to proceed to draw out the circuit with the switch closed. All right, so the first thing we're going to realize is because the switch is closed, we're going to have that the primary side voltage V1 is going to equal the input source voltage Vs. And following this, because we know the property of the transformer, we're going to get that the secondary side voltage V2 is going to be the same as V1, but scaled by the turns ratio of N2 over N1. So this value is going to be substituting V1 equals Vs. The value of V2 is Vs times N2 over N1. Now, we want to check the state of the diode. So is the diode turned on or off? And we can determine the state of the diode by finding the voltage VD. And VD is going to be equal to negative V2 minus V out. And negative V2 is negative Vs N2 over N1 minus V out. And we know this is a negative quantity. Negative VO is also a negative quantity. So therefore, VD is a negative quantity. If VD is a negative quantity, that confirms that the diode is off, and we're representing it in this case with the open circuit. Because the diode is off, that means the current going through the secondary side is 0. Now, for a transformer, we know that if the secondary current is 0, which is the current coming out of the dot of the secondary side, that implies that the current going into the dot on the primary side is also equal to 0. So therefore, during this dt interval, we simply have current circulating through Vs and the magnetizing inductor. And this is our analysis for this first state with the switch closed. Okay, now the next step is to analyze the circuit when the switch is open. And this is during our 1 minus dt interval, or the d prime t interval, with the switch being open. So here's the circuit in the d prime t interval when the switch becomes opened. Now, the thing to note is in the previous state, we had a current going through the magnetizing inductor. Now, we know the current cannot change or change abruptly in the inductor. So in this case, when the switch becomes opened, we still have a current flowing in the magnetizing inductor. Now, because the switch is open, it can't go through this path. So the magnetizing current therefore goes through in this path, through this ideal transformer winding here on the primary side. Now, because a current is entering this undotted terminal of the transformer on the primary side, we know that the current must be leaving the undotted terminal on the secondary side. So because the current is leaving here, we need the diode to turn on, and thus the diode is turned on in this case. So with the diode being turned on, we now have the voltage V2. V2 is going to be equal to the negative of the output voltage. So V2 equals negative VO. Now, because we know V2 equals negative VO, by the property of the transformer, we have V1, the primary side voltage, equals N1 over N2 times V2. So this means that V1 equals negative N1 over N2 VO. So now we can determine the conversion ratio because we have the primary side voltage V1, which is also equal to the voltage across the magnetizing inductor. In both the d prime t interval and the dt interval. So because the magnetizing inductor voltage VLM is equal to V1, we know that for this inductor, by the volt-second balance for DC-DC converters in steady state, that the voltage across an inductor, the average voltage across the inductor equals 0. So in this case, the average voltage across the inductor in the D interval, we had V1 equals Vs. And then in the D prime interval, the voltage was equal to negative N1, N2, VO. So this equals 0, and therefore we can solve for the conversion ratio of VO over Vs. So let's proceed to solve for that. So we have D times Vs equals 1 minus D times N1 over N2 VO. And we want to solve for VO. So divide both sides by this quantity, and we get N2 over N1 times D over 1 minus D times Vs. So this is our conversion ratio here. So we have the same conversion ratio as a buck boost converter, the D over 1 minus D term. But then we also have the transformer turns ratio, N2 over N1. So it's basically the same conversion ratio as a buck boost converter, but we have this additional scaling factor, N2 over N1. Okay, so in terms of the other quantities that we can express in the d prime t interval, so we have in this case the diode current ID. ID is just going to be the magnetizing current ILM scaled by N1 over N2. And that's simply because of this property of the transformer scaling this current by N1 over N2 to give us the current on the secondary side. And then another thing we should express is the switch voltage. And the switch voltage is going to be Vs, the input voltage, minus the primary side voltage V1. So that's going to be equal to Vs minus V1. And we know the value of V1, which we just calculated, was negative VO N1 over N2. So that means that the switch voltage is going to be Vs plus VO N1 over N2. And this is an important result because it tells us the stress that's on our switch. So when the switch is off, it's basically blocking this much voltage. The input source plus the output voltage times the turns ratio. And this means that this voltage that the switch is blocking is quite high. It's greater than the input source voltage. So that means, for example, just as an example, if N1 and N2, the turns ratio, let's say the turns ratio was just equal to 1, and the output voltage, let's just say as an example, V out is equal to the source voltage Vs, then in that case, as an example, V switch would be equal to 2 times the source voltage. So in this flyback converter, the slight drawback is the high voltage stress that's the on the switch during this D prime T interval where the switch is off. So in this case, we found the expressions for the diode current and the voltage across the switch. Another thing to keep in mind is the current through the resistor. The current through the resistor is just going to be V out over R, simple Ohm's law. So this is V out over R. So thus we can find the capacitor current IC by KCL is going to be ID minus the current through the resistor, so minus V out over R. So we found the resistor current as well as the capacitor current. It's ID minus IR is equal to, we can plug in the expressions for ID. So these are the other expressions for the voltages and currents in the circuit. All right, so to draw some waveforms, let's consider um, the primary side voltage to start off with. So V1 during the DT interval, we know that the switch is on. So let's call this um, the primary side voltage. This is going to be equal to the source voltage in the DT interval. And then let's say in the D prime T interval, so this is the D prime T interval now. It's equal to, as we know, V1 equals negative N1 over N2 VO. And in the next cycle, it'll repeat again. And we know from just from volt-seconds balance across the magnetizing inductor that the average voltage V1 must be equal to 0. So that also means that the area here must be equal to the area on the negative side, just so the average voltage is 0. And now for the magnetizing current, we know because of the expression that VLM, which we know is equal to V1, is equal to LM dILM over dt. So we have that the derivative of the current magnetizing current is equal to VLM over LM. So in this case, when V1 is positive, we know that the slope of the magnetizing current is increasing. Let's call this the dt interval. So this is our magnetizing current. So in the dt interval, V1 is positive, so the magnetizing current is increasing with a slope of Vs over Lm. And then in the d prime t interval, we have a slope that's negative because V1 is negative. And this slope is equal to negative V1, negative N1 over N2 VO over Lm. So this is our waveform for the magnetizing current. And note, because we're analyzing this circuit in the continuous current mode, we say that ILM is positive, and ILM never reaches 0. Because if it reached 0, it would enter the discontinuous conduction mode. Okay, and one more thing is we can also say what the switch current is. So the switch current in the DT interval is just equal to the switch current I switch is just going to be equal to ILM in the DT interval. And then we know in the D prime T interval, it turns off. So it's going to be equal to 0. And then once again, it will repeat like so. So in this case, I switch equals ILM, the DT interval, and is equal to 0 in the D prime T interval. And if we want to look at the diode current is going to be equal to 0 in the DT interval. In the D prime T interval, we know that we have solved for ID as the magnetizing current times N1 over N2. So it's going to be some scaled version um, like so. So I diode is equal to N1 over N2 times ILM in the D prime T interval. So these are some of the waveforms we can draw for the flyback converter. And the next step is we're going to take a look at what the minimum inductance that we need is to ensure that the flyback converter operates in the continuous conduction mode. To start this analysis, we want to find the average value of the magnetizing current, so ILM. And basically our strategy is to find the minimum magnetizing current as the average value, ILM, so this would be ILM, this average value, minus the change in the magnetizing current over 2. So in essence, we have the average values here, and we want to subtract this value here to get the minimum value at this point. So this would be change in ILM over 2. So to start by finding the average magnetizing current, we can use the observation that the source current, which is also equal to the switch current, is going to be equal to D times the average value of the magnetizing current. And we can see that from this waveform here, because the average value here in the D interval is the same as in the case for the switch current. But because the switch current is only on during the D interval, we're simply going to have this relationship here. And now, proceeding from here, another fact that we're going to leverage is that the output power is equal to the input source power. So the source power PS equals the output power PO. And we're going to have the source voltage times the average source current is going to be equal to the output voltage squared over the load resistance. And now we can plug in some values. So in this case, we're going to keep VS, and then IS, which is also equal to I switch, is equal to D times ILM. And we have this v out squared over r. And now we can express ILM as v out squared over r, and then divide both sides by vs over d. And now there's one more thing we can do. We want to get rid of vs in this. So we can substitute from our conversion ratio. We can substitute vs equals vo times n1 over n2, 1 minus d over d. So let's just bring this over. So if we substitute this in, this is going to give us, let's see. So we have the V outs will cancel, and we will be left, the D's will cancel. So we're going to get VO over R times N2 over N1 times 1 minus D. Okay, so this is one way to express the magnetizing current in terms of the output voltage VO. Actually, we might want to express the magnetizing current ILM in terms of VS, the source voltage. So once again, we had ILM is VS squared R times VSD. And now let's say we use the expression for VO instead. So we had VO was equal to VS D over 1 minus D times N2 over N1. And this was squared over RBSD. So this is going to give us, let's see, so we're going to get VS squared. That's going to cancel out with VS on the bottom. And we will have R still on the bottom. The D squared will cancel out with the D on the bottom. And we will get a 1 minus D squared on the bottom. And then we will have the turns ratio squared. So this is one way we can express ILM in terms of the output voltage. Another way is to express the magnetizing current in terms of the source voltage Vs. So we're going to go and use this second expression that we found. So now we have the average magnetizing current. Now what is the delta magnetizing current? So change in ILM. So we know this is what we want to look for. And we know the inductor characteristic equation is VLM equals LDIL over dt. In the dt interval, we have L equals the change in ILM over dt. And VLM during the dt interval is just equal to V1, which is equal to Vs in the dt interval. So therefore, the change in magnetizing current is equal to Vs dt over Lm. We can put the t on the bottom, so we get Vsd over Lmf, the switching frequency. So now we can write ILM min is equal to the average minus the delta over 2. So this is going to give us VSD over R times 1 minus D squared, N2 over N1 squared minus VSD over 2 LMF. Now, in the boundary case where we have continuous current mode, continuous mode to discontinuous mode, in this boundary case, we're going to have the minimum magnetizing current equal to 0. So if we set this expression to 0, this will solve for the minimum magnetizing current. So in this case, if we set this equation to 0 and solve for Ln min, we're going to do this out and get Ln min equals 1 minus d squared r over 2f n1 over n2 squared. And this we can see because these two terms will cancel out when we move this to here. And then we multiply by 1 minus d squared r on both sides. And this is our resulting expression. So this tells us the minimum magnetizing, min magnetizing inductance needed to operate in continuous mode. If we choose a magnetizing inductance that's smaller than this value, we'll begin to see discontinuous operation. So overall, this is the analysis of a basic flyback converter operated in the continuous current mode. We've derived the conversion ratio as well as solved for some of the current and voltage waveforms in this circuit. Now, one thing to note is that this flyback converter, the conversion ratio is basically that of a buck boost. So D over 1 minus D is a buck boost conversion ratio, but we additionally have this transformer turns ratio N2 over N1. And this gives us some advantages, like we can get larger step up or step down ratios compared to a buck boost. And another thing to note upon review of this circuit is that in the DT interval, we have the current charging this inductor here. So it's ramping up the current, the magnetizing current is ramping up. And in the d prime t interval, we have the magnetizing current is then ramping down, and we have that current going to charge the output in this case. So I hope you found this video analysis of the flyback converter helpful for your studies in power electronics. And if you'd like to watch more videos like this in the future, please give the video a thumbs up and subscribe to the channel. Thank you.